Good day everyone. In today's lecture, we'll be discussing about phase control converters. As we all know that phase control converters have many different type of circuits. So in this lecture, we'll basically be dealing with half wave converters. When the half wave converters are connected with R load, how it will perform. Then we'll discuss how it will perform when RL load is connected. Then further going, we'll be discussing about when RL load is connected and a freewheeling diode is also connected. And at the end, we'll be discussing about a half wave converter when an RLE load is connected to it. Let us start discussion with a single phase half wave converter with connected R load. Now here we can see that it is half wave. So half wave means either the positive half cycle or the negative half cycle conduction will be there. So here in my case we are having only positive half cycle conduction, and for negative half cycle there is no conduction. So here we can see that in this diagram I only have one SCR, that is the number of SCR is 1, which means that it will conduct only for the positive cycle. Now moving further, we should know about one more thing, that is for firing angle. So firing angle is nothing but, for example, if this is my waveform, positive half waveform, if I had connected a diode, what would have happened? From 0 to pi my diode would conduct, but this is a thyristor that I am conducting. So at instant 0, thyristor T is forward biased, but it is not turned on. For turning it on, I have to give a gate pulse. So I am giving a gate pulse at this instant. So when I am giving a gate pulse, at that instant my thyristor will turn on. So I can see here that from here my thyristor, I'll get this portion of the output. So let me take this angle to be 0 and let me take it to be alpha, and let me this is pi. So from this discussion we know that if a diode I had used, it would have conduct from 0 to pi. So thyristor is conducting only from alpha to pi. Now we can see that there is a gap. This gap 0 to alpha, this alpha is called as my firing angle. So firing angle is nothing but the angle between the instant a thyristor would have conducted if it were a diode and the instant it is triggered. So here I can see that my thyristor is triggered only at alpha. So if I am taking the difference between 0 and alpha, I get alpha. So this alpha is called as my firing angle, or the angle from at which instant my thyristor starts conducting. And one more thing that we have to note here is that now if I am giving the alpha at this duration, I'll get this portion of the waveform, that is, for example, let me take it to be 75% of the at alpha 1. If I am giving alpha 1, I will get 75% of the power. The same thing what I am doing is I am increasing my alpha's angle and I am making it here. Let me take it to be alpha 2. So when alpha 2 is there, we can see that I will get only this portion of the output I will be getting. So at alpha 2, I will get only 25% of the power. So from this it is quite clear that if I am varying the angle alpha, I can control the load current and the load voltage. That is the output, what output I am getting, I can control that. Now here we can see that there is only one pulse. Why there is only one pulse? As only one thyristor I am using. For triggering one thyristor, only one gate pulse is required. So this is a one pulse converter. Now let us look at the waveform. Now in this waveform, different quantities that we have is Vs, that is my source voltage. Source voltage I am using a AC quantity, so it is a sinusoidal quantity, which means that Vm sin omega t is my source voltage. Then I have Ig. Ig is nothing but the gate pulse that I am going to give to my thyristor T. Then I have V0 and I0. This is my output, and this is Vt, what voltage is appearing across the thyristor T. Now let us check how this circuit is working. Now here we can see that at omega t is equal to 0, at that instant my thyristor T, it will become forward bias. Now when my thyristor T is forward bias, it has not started conducting. Looking at the output waveform, we can see that only dotted line is there. This is the output that I am getting, that is, there is no conduction. Now when I am giving the firing pulse, that firing pulse is given at angle alpha. So at alpha my thyristor will turn on. So I can see here that from alpha I am getting my output only up to pi. At pi, what will happen is my supply will reverse. So when my supply is reversing, it means that my thyristor has been reverse biased. So when my thyristor is getting a reverse bias, it means that my thyristor will turn off. So that is why I am giving 0 output I am getting. Again I have reached 2 pi. Then at 2 pi, one cycle is completing. Again it is forward bias. Then at alpha, 2 pi plus alpha, it is turning on and I will get this portion of the output. Now I am using a R load. So R load means that the voltage and current will have characteristics which are in phase, which means that, so if my voltage V is achieving maximum, my current I will also achieve maximum at the same instant. So we can see here that when my voltage is achieving maximum, at the same instant my current is also achieving maximum. So I can say that this is the characteristics of a R load. Then this thyristor, that is from 0 to alpha it was off, from alpha to pi it was on. So it means that there is a voltage across the thyristor from 0 to alpha. Now when the thyristor is turning on, it means that it is just providing a path, so that all the voltage drop or all the current is appeared across the load. So during this instant we can see that there is no voltage across the thyristor. Why? Because it is conducting to the load. At this duration we can see that my thyristor is off, therefore some voltage is appearing across my thyristor. So I can clearly see that Vt waveform I can get source minus output. If I am doing this, I will get my thyristor voltage. So this is my source voltage, this is my output voltage. I am subtracting output voltage from my source voltage. So I can see here that this portion will get removed. Why? Because during this portion my thyristor is on, and the remaining portion I will get it as the voltage across my thyristor. Now moving further, we know that we have to find out some expressions for this thyristor, for the operation of this thyristor. So from the diagram it is quite clear that my SCRT, it operate, that is if I am considering one cycle, if I am considering, so in this cycle it operates from 0 to it operates from alpha to pi, that is from alpha to pi my thyristor is conducting. So what I have to do for finding out the area under this curve, I have to integrate. So integrating limit is from alpha to pi. This is the limit. So what I will do is to find out the average load voltage V0, I will integrate it for the cycle. I am finding out the average, therefore 1 by 2 pi. The limit is alpha to pi, and I know that Vs into d omega t. Vs is nothing but Vm sin omega t. So when I am integrating this, I get V0 is equal to Vm by 2 pi 1 plus cos alpha. This is the output average load voltage that I will be getting at the output side. Now if I found out V0, I can easily find out I0. How I can find out I0? I0 is nothing but V0 by R. If I am using a simple Ohm's law, I can find it out directly. Then if I have to find out my RMS voltage value, what I have to do is, for example, what I will do is, I will just 1 by 2 pi, I will square it, that is from limit Vs squared d omega t square root of the whole thing. Square root of the whole thing if I am taking, I will get my RMS value. So the RMS value comes out to be, after solving it, integrating and solving it, the RMS value comes out to be Vm by 2 under root of pi pi minus alpha plus 1 by 2 sine 2 alpha. This is under root. So this is the value of RMS output voltage value that I am getting. Now if I know the RMS output voltage value, current value can easily be found out, VOR by R. Now if I have to find out what is the power delivered to my load, the power delivered to my load is nothing but VOR into IOR. Then if I have to find out my power factor, I can simply write VOR by VS. If I have to find out the input volt amperes, I can write it to be Vs into OR. So it is quite clear that if I can find out the value of VO, or if I am able to find out the value of VOR, I can easily calculate IOR, the power delivered to load, and the power factor easily I can calculate. So further we will not be discussing about all these values, because this is the very basic that we'll be using in every converter circuit. Now we'll move on to the next circuit. Now the next circuit that I have is nothing but a single phase half wave converter, but this will have RL load. RL load means what? That is the load in my load in the previous I was having only a resistor. Now here a inductor as well is added. So we clearly know that the characteristics of an inductor, in inductor the current lags the voltage. That is, if it was a pure inductor, it would have lagged by 90 degree, but this is not a pure inductor. Why? Because in this total combination, if I see, also a R component is also there. So here we can clearly see that there will be some changes in the output waveforms that I am getting. Now as in the previous, let us look at the waveform. This is my source voltage, this is output, that is output voltage, output current, and VT, that is the voltage across the thyristor T. Now here we can see that when the omega T value is 0, it means that my thyristor is forward biased. So thyristor is forward biased, but it is not conducting. When I am giving firing pulse at alpha, my thyristor it will turn on, then up to pi my thyristor will conduct, and at pi my thyristor will become reverse bias. So it means that my thyristor is turned off. But we can see here that as I am having a inductor, when the current was flowing in this path, the inductor stored some energy inside that. So what it will do is it will discharge the energy. That is, at pi interval my thyristor is turned off, but the stored charge in the inductor, this is responsible for this portion, this small portion that I am getting, and at angle beta this conduction will stop. That is, at angle beta this conduction will stop. So this up from pi to beta, there is a current flow because of the energy stored in the inductor. Beta is nothing but my extinction angle, and I can find out the conduction angle, that is for what duration my thyristor is conducting. So here it can be clearly seen that my thyristor is conducting from alpha to beta duration, that is current is flowing from alpha to beta duration. So here we can clearly see that if I have to find out my conduction angle, I have to subtract beta minus alpha. So this is called as my conduction angle. Gamma is nothing but for what duration my thyristor is conducting. Now if I have to find out the average voltage, average output voltage, average, that is for a cycle 1 by 2 pi, we know that alpha to beta conduction, my thyristor is conducting from alpha to beta, Vs d omega t. Vs is nothing but Vm sin omega t. When I am integrating that, I get Vm by 2 pi cos alpha minus cos beta. Now if I know what is the value of V0, I can easily calculate I0. I0 is nothing but V0 by R. Then VOR can be calculated. If VOR I know, I can easily calculate the value of IOR. So in this manner I can calculate all the other expressions that are needed. I can calculate. So VT is nothing but the what is the remaining. So here we can see that up to this portion there is conduction. So this waveform in R it was in this manner, but here it is a straight line, then it is increasing in the negative direction. So that this is the only difference between a R load and a RL load. So in RL load, we'll get a small discharge portion because of this energy stored in the inductor. The next type of load that we have is single phase half wave converter. This is also having RL load only, but here a freewheeling diode is also connected. So with RL load, I am also connecting a freewheeling diode. So freewheeling diode is nothing but a diode through it which gives a path for the energy stored in the load portion to discharge. Now here we can see that as in the previous diagram, we can see that here we had a small portion in the negative half. So this small portion in the negative half, this is removed. Why this is removed? Because when my thyristor is reverse biased, my thyristor is turned off, but the energy stored in the inductor that should discharge. In the previous case, as no freewheeling diode was there, it discharged through this using this thyristor only. Now what is happening? As a freewheeling diode is there, it will flow in this path. That is, it will leave the thyristor. So we don't get a negative small portion in the negative half. So in the previous, as I was saying, as it is RL load, current will lag the voltage. Current will lag the voltage. So here we can see that when voltage is achieving maximum, at that instant current is not achieving maximum. So we can see that looking at the maximums of output voltage and output current, the current is lagging. Why this is lagging? Because the load here is RL load. So in this similar manner, here also we can see that the maximum is not the same. That is, there is a discharge, but this discharge is because of the freewheeling diode. So we can see here that from alpha to pi, my thyristor T is conducting, and from pi to 2 pi plus alpha, my freewheeling diode is conducting. So from this it is quite clear, thyristor is conducting and freewheeling diode is also conducting. Vt, as I said earlier, Vt is nothing but Vs minus V0. I'll get my Vt's duration I'll get. So in the previous graph we can see here that here Vt had a clipped portion, but here we can see that it is not having a clipped portion because freewheeling diode is overtaking in this duration. The next type of half wave converters that we are having, loads that we are having, is Rle load. So R is my resistive component, L is my inductive component, E is, for example, if I am using a DC motor, sometimes if I am using a DC motor, a back EMF will be generated. Now this back EMF will be representing it in the form of E, that is a battery E connected across the load. Now let us consider about how the single phase half wave converter will work with Rle load. So here we know that as I am having RL, this means that my current will lag my voltage. Current will lag the voltage by somewhere between 0 degree to 90 degree. Then I also have a E. Now this E is, we can clearly see that E is in opposite, that is the connection of E is in opposite direction to the current that will flow. Now here one thing that we have to take care is that I have to find out one angle theta1. Now what is theta1? Now let us look at the diagram. Now here we can see that this is my source voltage Vs, and to Vs, in the Vs diagram I can see a constant level E. E is nothing but the voltage level because of my battery that is connected, E. Now here we can see that E and this sinusoidal wave, it is getting intersected at a point, and that angle corresponding to that is theta1. The angle corresponding to the point where my E and sinusoidal voltage is intersecting each other, that is theta1. Now I have to find out what is my angle theta1. Now to find out theta1, what I can do is I can write Vm sine omega t, or the angle that I am going to find is equal to E. So using this expression I can clearly find out that theta 1 is equal to sine inverse E by Vm. Now from this expression I can find out the value of my theta 1. So when I am using Rle load, I have to find out the value of theta 1 because theta 1 plays a very important role in the operation of an SCR when I'm talking about a single phase half wave converter with Rle load connected. Now for example, if I am giving a firing pulse which is less than theta 1, we can clearly see that my SCR will not turn on and my SCR will remain reverse bias. Why? So here we can see that now for example, this is theta 1. So before theta 1, firing angle is given before theta 1. Let us take at this instant I am giving my firing angle. So when I am giving my firing angle, my thyristor is trying to turn on, but the opposing voltage is more. So because of that, my thyristor will not become forward biased. Why? Because the E level is more than the level that is the more than the current that is flowing across the SCR. So because of that, because of that, my SCR will turn off. That is, current is flowing, trying to flow in this direction, but E is opposing. Now this the value of E, the current that is flowing because of E is greater than the current that is flowing because of T. Because of that, it will turn off. Now what I have to do is I have to find out a firing pulse which is greater than theta 1. So if firing pulse that I am giving is greater than theta 1, that is the alpha that I am giving is greater than theta 1, my SCR will turn on. So this is the very basic criteria that we have to keep in mind. That is, if I am using Rle load, always my firing pulse should be greater than my angle theta 1. So if it is greater than theta 1, then only my SCR will turn on. Now here we can clearly see that at after theta 1 and alpha firing pulse is given. So from alpha, my thyristor it is starting to conduct. At pi it is reverse bias, but because of the inductor I am getting the small portion in the negative half. In the previous diagrams, that is, let us consider Rle load. Now here in Rle load, what happened? This level was 0, but here in Rle load, this level is not 0. It is maintaining a E level. Why? Because already a source is connected E, which is supplying voltage up to this level. So because of that, I will not get any 0 levels. I will not get. Now looking at the maximum, we can clearly understand the output voltage maximum and the output currents maximum are not at the same angle. That is, here current is lagging the voltage. That is because a RL component is there in my load. Then we can see here that the VT, let us look at the VT in a RL load. So this is the VT in a RL load. It is starting from 0. But here we can see that it is not starting from 0, it is starting from a point lower than 0. That is, as the source voltage is opposed by the battery, it is starting from a lower level E. That is the waveform, the 0, it should have been at this point. The waveform is completely shifted down by a level E. That is what EMF E level is given by the battery. It is shifted down by that level. Now to find out V0 here, we can clearly see that my thyristor conducts from alpha to 2 pi plus alpha. So it is clearly seen that from alpha to 2 pi plus alpha my thyristor is conducting, or the voltage is not becoming 0. Now for this duration, I can clearly write V0 is equal to 1 by 2 pi, complete cycle I am taking. Now in this cycle, from alpha to beta, beta is the angle where my thyristor should have turned off. This is the angle where my thyristor is turning off, and from after beta, E is taking over. So alpha to beta, I can write Vs d omega t. Now other than that, one more component I am having, that is battery component. Battery is conducting from 2 pi plus alpha minus beta. Now this is the duration. This is the duration that I have considered, that is, this is a duration of 2 pi, or duration of 2 pi I have considered. Now in this duration I can clearly see that from alpha to beta my thyristor T is conducting, and from beta to 2 pi plus alpha my EMF E is conducting. To find this gap, what I have to do? I have to write 2 pi plus alpha minus beta. That is why I am getting the previous expression I am getting. Now solving that, I get 1 by 2 pi Vm cos alpha minus cos beta. This is the component because of my thyristor, and because of the battery, the component that I am getting 2 pi plus alpha minus beta plus E into 2. This is the value of my V0, average voltage. Now in all these four circuits, one more thing that we have to discuss is my circuit turn off time, TC. Circuit turn off time is nothing but the duration for which my SCR is reverse bias. For what duration my SCR is remaining reverse bias. Now looking at the first, that is half wave converter with Rle Load, we can clearly see that from pi to 2 pi my SCR is turned off. So I can clearly write TC is equal to pi by omega second. The circuit turn off for a half wave converter having Rle Load is TC is equal to pi by omega. The next that I'll consider here is a Rle Load. Now in Rle Load I can see that from beta to 2 pi, this duration my SCR is remaining reverse bias in this duration, because at 2 pi again SCR will become forward bias, but it is not conducting because there is a lack of gate pulse. So here clearly I can write TC is equal to 2 pi minus beta divided by omega second. This is the circuit turn off time for a single phase half wave converter having Rle Load. Then we have Rle Load with freewheeling diode. The characteristics is almost similar to that of a Rle Load. Therefore, TC is equal to pi by omega in this case as well. Then the next thing that I am having is a Rle Load. So in TC for Rle Load, I can write 2 pi plus theta 1 minus beta by omega. So clearly we can see here that my SCR is reverse bias up to this duration. Why up to this duration? Because this firing pulse alpha, let me consider my firing pulse alpha. Now before this firing pulse alpha I am having a duration theta 1. Up to this theta 1 duration, E, the level of E is greater than the level of Vm by sin omega t. So only after theta 1 my SCR it will become forward biased, or there will, my SCR will get a forward bias. So therefore I can write from 2 pi plus theta 1 minus beta. In this duration my SCR is, that is, for example, this is 2 pi plus theta 1 and this is the duration till when my SCR is conducting. So this gap I'll get it to be the circuit turn off time, TC. So here we can see that why TC is required. We know that TC is nothing but the circuit turn off time. As similar to circuit turn off time, I have turn off time of my thyristor. Now the circuit turn off time should be greater than the turn off time of a thyristor for satisfactory commutation. If the value of TQ is not less than TC, I'll get a commutation failure, or my SCR will not turn off and there will be short circuit across my circuit and my circuit will get damaged.